This is work I did in collaboration with Bryan Ford and Daniel Jackowitz at Yale University. Let's consider a scenario where we have Alice who's browsing the web, and she browses various different websites such as social networks, blogs, videos, and she'd like to do that without her ISP knowing which website she's accessing. At the same time, when she's accessing the social network, she's doing so underneath the use of a pseudonym. And she'd prefer that the social network, say Facebook, doesn't actually know her real identity by examining her IP address and tracing that back to her home or what have you not. In addition, as she browses questionable content on the blogs and the videos, she would prefer to do so anonymously. In the scenario up here that I presented, there are no protections for Alice. She's easily identified and de-anonymized. However, Alice is a clever user, and she employs anonymous communication tools such as Tor. And Tor works so well that adversaries don't really target Tor. Instead, they target the user's environment. This has become so predominant that if you were to look through publications, both academic and journalistic documentation, you'd see that there are a dearth of publications discussing where users have been de-anonymized while using Tor because of issues in the Tor system itself. However, there are a plethora of publications discussing how users have been de-anonymized due to their user environment. And we call this the leaky boat of the anonymous communication systems. To address this, we introduced Nimix, an operating system that provides system-enforced isolation, effectively placing each one of the browsing instances into separate environments called NIMs. Each one of these NIMs offers an amnesiac browsing session. Effectively, at boot time, each of these NIMs are identical, and they collect state over time. This is their browsing session state. And upon turning them off, all that state is securely erased. In addition, Nimix also provides the ability to store content for longer periods of time through anonymous cloud storage, details of which I'll go on throughout the discussion of the presentation. In the presentation, I'm going to first discuss various types of user environment attacks that effectively de-anonymize the user. I'll then discuss the Nimix architecture and show you exactly how the Nimix architecture protects against these types of attacks. I'll then show you some evaluation numbers using a real practical Nimix implementation and have various discussions on future directions. The first attack that I want to focus on is an application level attack. In this scenario, we have Alice, who's in Repressistan, and communicates with her beleaguered allies using a blog hosted in Freetopia. And since, again, Alice is a clever user, she employs the Tor browser bundle, which basically encapsulates a Firefox and Tor instance together and ensures that she's communicating securely through Tor. And therefore, the glorious leader of Repressistan can't easily identify Alice's actions as she's using the blog to communicate with her allies. However, this glorious leader of Repressistan has hacked into the Freetopian blog. Say there was a PHP blog that it took advantage of, and installed a JavaScript exploit. Now, when Alice visits the website the next time, this JavaScript exploit will run remotely on her machine, causing her machine to communicate directly with the glorious leader's booby trap, effectively de-anonymizing her by sharing her public IP address with the glorious leader. Now, she was de-anonymized despite the fact that she was using the Tor browser bundle, using the Tor communication tool. And this is very similar to an event that recently happened when the FBI hacked into the Freedom hosting site and effectively de-anonymized many users. The next attack I want to focus on is a correlation attack. And in this scenario, we have Bob of Freetopia. Bob is a very successful businessman. He runs a blog that has various important things of the day, and he also has a very active social life. But he doesn't want to mix the two of them. So he employs a tool like Tor to provide this isolation, this anonymity, if you will, to isolate his different identities in these environments. And as Bob is browsing these sites, he notices there's a login by Facebook on each one of these sites. And he knows better than actually logging into Facebook because that would basically link all of his identities on these various sites together. However, despite the fact that Bob is using Tor, because Facebook has access to all of his different browsing sessions and they're all running on the same browsing instance, he's effectively de-anonymized, or his identity is correlated because of the shared browsing state. And again, this is despite the fact that Bob was using Tor. The final scenario I want to consider is a case of Carol of the land of Opportunia. And she's traveling back from a recent trip to Fruitopia and has to pass through Border Patrol. And Border Patrol is going to insist that it has access to Alice's hard drive. Unfortunately, Alice has a strange fetish. She's into sexy cat pictures. And while this is just sensitive information, it's not necessarily illegal, she's not very comfortable with sharing this publicly. And effectively, the Border Patrol is going to insist that either he has access to her contents, potentially publicly shaming her, or she's going to be spending a few nights in prison until she finally relinquishes. To recap, I went over 3 types of attacks. I began with the application level attack, where the glorious leader focused on the Firefox instance running inside of Alice's machine. Then I discussed the correlation attack, where an overaggressive or omniscient advertiser, or I mean social network, was able to identify Bob despite the fact that he was using Tor. And finally, I discussed the confiscation attack, where the Border Patrol insisted on having access to Carol's machines, effectively, in all these cases, revealing information that the users would have rather kept private. Now that I've introduced these various user environment attacks, let me discuss how Nimix architecture works and begin to paint a picture of how we provide protection for the user environment. As I stated earlier, Nimix provides this system-enforced isolation. As you can see, we have various different NIMs. Each one of these NIMs is a separate browsing environment consisting of a unique virtual machine with completely isolated state, so that no 2 browsing sessions will ever have any overlapping information. In addition, when we start these virtual machines, as we turn them off, the entire state is securely erased. And of course, we have the anonymous cloud storage so that we can retain information over longer periods of time without keeping that on our local machine, thus providing us some strong plausible deniability that we never even used Nimix in the first place. In addition, Nimix also has a component for data sanitization. This basically would allow us to share our local content on our machine safely without de-anonymizing us into the internet. Now let me work you through a few examples of how Nimix works. The first example that I want to discuss is the ephemeral NIM. Effectively, this is the default browsing state of Nimix. So if Alice were to start Nimix, she'd select the option Start a new browsing state, or Start a new browser session. In doing so, Nimix would begin a new NIM. And each of these NIMs begins, like I said, with the same base state consisting of 2 virtual machines. You might ask, why do we have 2 virtual machines? The reason is because we want to isolate the user's browsing experience in the anon VM and make sure it's completely separated from the communication tool. Thereby, the browser, or anything running inside that environment cannot directly communicate with the internet. It is effectively forced completely through the communication tool. And another thing I want to mention about this is that all the virtual machines and the entire system uses a common base image. And we use something called a overlay file system or union file system to merge multiple file systems together. For each one of these different systems, we have a configuration file system that tailors it towards its specific task. For example, we have a unique file system for each anon VM. And then we layer on top of that a copy on write file system that, of course, when the system is turned off, is securely erased, leaving no trace behind. Now let's say that Alice instead desires to use a long-lived NIM. Effectively, she wants persistent state. And reasons for doing so include that she might want to keep her bookmarks, her login information, and other important features or tools that she doesn't want to have to reinstall every single time she restarts a NIM. In addition, there's also a huge attraction to having this persistent state for the conv VM. In fact, recent research has shown that by continuously resetting our communication tool, our anonymous communication tool, we can actually weaken the user's anonymity. To do so, we anonymously store and restore NIMs from the cloud. Let me work you through an example. It begins by Alice starting Nimix and saying, I'd like to restore a NIM. She's presented with a NIM running in the background and a prompt asking, what cloud service would you like to download your NIM from? And she would select, say, the Google Cloud, or Google Drive, and input her credentials to access that image. The contents would be downloaded into the non-VM, copied from the hypervisor into the hypervisor, and effectively shutting down this temporary ephemeral NIM just for downloading this instance. And in its place, restoring a long-lived nym using the contents that were just downloaded from Google Drive. As soon as that's bootstrapped and up and running, she's able to resume her previous browsing session without interruption. In the final scenario, we have the issue of data sanitization, or the ability to share data. And you can consider, let's say Alice recently went to an event, say a big rally, and she snapped several pictures. And she wants to release these pictures on her blog, but she doesn't want to leak, say, metadata, personal information that are embedded in the pictures, such as the serial number of her camera, the GPS coordinates, so on and so forth. But she doesn't know how they're embedded in the picture. She just knows that they exist. So in Nimix, one of the key things is that we never put the local file systems inside any of the NIMs, because if doing so, if an attacker were to enter any of the NIMs, they'd have direct access to all those file systems and could potentially de-anonymize the user. Instead, we employ a sanitation VM that mounts all the user's file systems. The user can browse through that sanitation VM, select the files that they'd like to copy over into a NIM, which would result in a prompt asking, how would you like these documents cleaned? In the case of Alice and her images, it would say, she might select, I just like to have the pictures metadata erased. Basically, she knows the contents of the pictures are secure, so she's pretty happy with that. And as a result, the filtered files would then appear inside of her NIM, safely and ready, able to be uploaded to her blog through the NIM. So now that I've introduced Nimix, I want to walk you through those attacks that we discussed earlier and show how Nimix protects the user from those attacks. Recall we had the application level attack, the correlation attack, and the confiscation attack. In the application attack, just to remind you, we had Glorious Leader targeting the Firefox instance that effectively caused the Firefox instance to communicate outside of Tor and de-anonymizing Alice. However, had Alice been using Nimix, the Firefox instance would have been running inside of its own NIM, connected to a Tor instance running in a separate communication channel. And now, when Alice accesses the website, the blog hosted in Fruitopia, when the JavaScript exploit executes, it has no direct access to her network. And thus, the result is routed back through Tor and unable to de-anonymize her. Thus, Nimix has protected Alice from an application level attack. When we look at Bob and his correlation attacks with his successful business, if Bob were to actually have instead employed Nimix, each one of his browsing instances would have been executing in an independent NIM. And now, when he browses the various websites and the Facebook login pops up, he again can safely ignore it, but more importantly, each one of these different browsing contexts will appear uniquely to Facebook, and they'll be unable to correlate them as a single unique user. Instead, there will be 3 independent users. Thus, again, Nimix has protected against the correlation attack. Finally, moving on to the confiscation attack, recall Carol with her sexy cats. Now, if she had employed Nimix and stored the cat pictures inside of, say, a long-lived NIM, she could view the pictures safely while accessing that NIM, and upon terminating the NIM, those cat pictures would completely disappear from her machine, yet still be in the cloud so she can retrieve them later. And when she's passing through Border Patrol, she can say, here's my laptop. And the Border Patrol say, well, there's nothing on here. This is weird, whatever. And she'd move on, perfectly fine, no problem. Thus, we can see that Nimix is protected against all these various different types of user environment attacks. So now that I've shown you how Nimix works, I want to go over how it actually works when running on a real system. We've been developing Nimix for about 2 years now, and we began first with Ubuntu 12.04. We've migrated to Ubuntu 14.04. We use the virtualization system QEMU with support for hardware virtualization through KVM, and we employed the Linux kernel's overlay file system for union file management. We did evaluations using a modern desktop, connected to a test Tor deployment using Deterlab. The test Tor deployment had an end-to-end bandwidth limitation of 10 megabits and 200 millisecond end-to-end latency delay. We set the specifications for the various VMs. For the non-VM, we had 500 megabytes per NIM, and we had 150 megabytes for each of the communication VMs. In the first evaluation, we wanted to consider what's the CPU overhead, or more specifically, what's the browsing experience like as we scale up additional pseudonyms. And so in this evaluation, we employ the JavaScript benchmark Peacekeeper. And what Peacekeeper effectively does is benchmarks JavaScript from doing integer operations, graphical operations, what have you not. And we scaled this starting with a host system and then bootstrapped several nyms up to 8 nyms, as you can see on the x-axis. And on the y-axis, we show the accumulated score for the average Peacekeeper score in each one of these instances. And in comparing the actual or observed results with the expected, we can see that Nymix was able to match quite well with what we expected in terms of performance. In terms of memory usage, we analyzed how much memory is consumed by Nymix as we bootstrap additional nyms. In this graph, we have the number of nyms on the x-axis, and on the first y-axis, we show the total number of megabytes consumed by the entire system. Because Nymix has a lot of duplicated content, we employed something called KSM, or kernel shared memory. And this effectively allowed the Linux kernel to monitor the memory used by any operating system or any operations inside the system to reduce the amount of duplicated content. And the key thing I want you to focus on here is that if you look at the used memory versus the expected memory, we're about 10% lower than what we expected. And this is largely due to the KSM effect. Had we had a more intelligent manager for KSM, we probably could have had an even greater reduction in memory because there's a lot of read-only memory inside of Nymix. And thus, we'd probably be able to boot up even more nyms and consume less memory. The final evaluation focuses on network overheads, specifically how long it takes to download a Linux kernel from a server connected to the end of the Tor relay system that we had set up. In this evaluation, we downloaded from up to 8 nyms in parallel, as you can see on the x-axis, and on the y-axis, you can see the total time to download all of these different kernels. And the key thing here is that you can see that the delay between the actual and expected is very small, such to the point that we could almost argue it's negligible because in practice, Tor and other anonymous communication systems are oversubscribed. So with that in mind, I'd like to wrap up the talk with some discussion points. First beginning with what Nymix is. Nymix is not a complete solution. Instead, the real goal of Nymix is to provide a research platform for exploring pseudonymity using virtualization. There are a lot of other works in this field that are providing features such as hardened and amnesic environments provided by Tails, and also UNIX and cubes that offer anonymity-enforced browsing. In the long term, I think the goal for our research should be to integrate with some of these systems, namely perhaps Tails because of its well-hardened environment. And to do so, we have several questions that come up. The first of which is, what about the communication VM? Do we really need one COM VM per each of the nyms that we start up? As you can see, each COM VM isn't cheap. It's not free. However, having a single COM VM means that we're going to have shared anonymous communication state across all of our nyms. And in the case of Tor, that's not necessarily ideal. The next issue is, in the case of Tails, where it's a very well-hardened environment, reusing that base image might not be very practical, and it could be actually a very challenging task. Instead, it'd be more practical to bundle along another gigabyte image, which may not be too acceptable for users that don't have access to multi-gigabyte USB sticks. Finally, and perhaps more interestingly, is the persistence model. Obviously, we showed that the cloud model provides strong plausible deniability. However, it also requires a significant amount of bandwidth in order to download and upload your nyms over a period of time. However, if we were interested in perhaps an approach that offered less plausible deniability, but yet still offered some, we could envision that when a user boots Nymix, it will install an encrypted volume header that really links to nothing. So it's basically a dummy. And if a user wanted to, they could instantiate their own encrypted volume and replace this volume header. And thus, any user would have that plausible deniability that my system just came that way. Of course, now they wouldn't be able to say, I've never used Nymix. And there are, of course, further challenges in producing a system like Nymix that provides really strong pseudonymity. The first is that the user environment is still very fingerprintable. If an adversary gets access to it, they can run various CPU benchmarks, perhaps poke the CPU or other aspects of the system to identify performance numbers and use that to identify a user. Also, if an adversary were able to control of multiple NIMs, he could take advantage of VMM timing channel attacks to try to see if that's the same user, basically another form of correlation attack. In terms of providing better usability, we have the question of whether or not is there an effective means of connecting a user microphone or a video camera or anything like that to the user space inside of a NIM. And while we presented a mechanism of pushing data into the internet, we haven't come up with a satisfiable method of downloading content from the internet and storing it on our local media. So this basically concludes my talk. As I mentioned, there are various types of attacks on the user environment. In fact, we only went over a handful, and there's many, many more. But Nimix offers a practical approach to defending against these. However, even in the realm of pseudonymity and anonymity, there's a lot of attacks outside the scope of Nimix, and therefore we believe it's in our best interest to integrate with existing approaches. You can see our website as well as our code is on GitHub. Thank you very much.
Hello. So I had one question related to, you mentioned CPU fingerprinting, but it seems like this might also be susceptible to things like browser fingerprinting because you're using the same initial VM image to bootstrap all of these, right? So your browser versions are going to be the same, your resolutions are going to be the same. Have you guys thought about defenses against things like that?
Well, actually, that's ideal because all Nimix users will appear to be the same.
Assuming you have a large enough user base.
Oh, well, obviously, yes. That would be desirable.
But, well, so things like resolution, though, are still going to be a problem, right? Because that's essentially going to be dependent upon the underlying client and how big they maximize their VM windows. And if they do that with consistency, that could be a unique fingerprint.
Right. So one of the other aspects that would need to be hardened would be enforcing a fixed resolution inside the VM or within the VMs.
Thank you.
Mm-hmm.
So I have a question. If you allow VMs to communicate via channels other than the file system, would it need to protect against that? For example, if I open a socket to a different VM. Right now, your sanitization seems to work at the file system layer.
So I'm not quite sure the example that you're coming up with where we would have, I mean, that's not in our model that we've thought up to this point in time where we might have two VMs, I guess, communicating directly with each other.
So you just disallowed it?
So each one of these NIMs are running isolated. I mean, obviously, in order for the COM VM and the non-VM to communicate, they have a single bidirectional pipe between the two of them. But that's enforced so that only the two of them are on that channel and no other parties can access that except for the hypervisor. And of course, if the hypervisor is compromised, then there's no point in having the system whatsoever.
Actually, they could talk to each other via sockets, but then they would both be ferried through two different Tor connections. Right. So they would be, kind of like two Tor services talking to each other.
Yeah, so this is cool work. One question I had is, in your correlation attack, it seems like you're assuming that each NIM connects to a specific site. And I was wondering if it'd be possible for a user to browse multiple sites within a single NIM session.
Right, there's no limitation on how they use the NIMs. So in some aspects, it's up to the user to enforce their own pseudonymity. So if a user were to accidentally, say, load up two differing identities inside the same NIM, right, they'd effectively revert back to de-anonymizing themselves or correlating themselves.
Yeah, that makes sense. So it's not like you recognize that you're loading a new domain and then you launch a new NIM to handle that new session with a new domain or anything like that.
Well, that would be part of the benefit of using the long-lived NIMs. Therefore, if you were to set up one of these states and you said, I'm never going to go and log into another session inside this state, that would be at least one mechanism of hopefully preventing the user from accidentally shooting themselves in the foot.
Okay, thanks.
Mm-hmm.